Okay, Organic Chemistry 2343. We're going to continue with our last section of chapter 20 on amines, additional reactions with amines. Okay, so in the last one, we figured out how to make aryl diazonium salts. So let's figure out what else we can use them for besides a simple displacement to create those systems. So once we form this aromatic diazonium salt using an aromatic amine with the in situ created nitrous acid to create our diazonium here. Remember, that's a great leaving group. That nitrogen 2 is a great leaving group. And so we can displace it with a lot of really interesting nucleophiles. So in the case of copper oxide and water, with water as our nucleophile, we can end up with phenols or hydroxybenzene derivatives. By adding a halide, either copper halide or bromium or copper bromide here, we can get to the chloro and bromine directly. Notice this is similar to it. This gives us the same property as this. We're using chlorine and ferric chloride or bromine and bromic chloride. However, we don't have to worry about orthopara direction because we're actually only displacing where the amine was on the benzene ring. We can also use cyanide as a nucleophile here to generate our cyano compound right here. Now, unlike the system where we had halogenated with ferric chloride or ferric bromide, we didn't do that with iodine or bromine. This way, using the diazonium salt, we can create an aryl iodide and aryl fluorides for the first time. We weren't able to do that before. We will be able to do now. In addition, we can use a strong acid like phosphoric acid to put a hydrogen on that benzene ring wherever that amine was. So there's a couple reasons to do that, and we'll get into that in a couple slides. Okay, so the first reaction we want to talk about here is what we call the Meyer reaction. And this is the reaction of diazonium salts with either copper bromide, copper chloride, or copper cyanide. Okay, so in this case right here, what we would do is we'd take any amino benzene compound we have right here. We would create our nitrous acid in situ with HCl and sodium nitrate. And that would create our diazonium salt. And then warming it lightly with copper chloride would generate our chlorine derivative here. Notice it's wherever the nitrogen was on the original material is where the chlorine gets. We don't have to worry about orthopara, we don't have to worry about direction. It goes exactly where the nitrogen was on the previous material. So that makes it very synthetically useful, and especially if you're directing it exactly to where you want it. Okay, so in addition to putting chlorine on there, we can do bromide on there, and the only difference is the substitution of copper bromide as the source of the salt. Note this is a little higher in temperature, but it does get to the correct product. And again, it's substitution directly where the amine group was on the benzene ring. Okay, we can also use this with copper cyanide as our nucleophilic source, and that gives us a nitrile right here. Let's say you're trying to get to a cyano, or I'm sorry, not. You can then convert your cyano group to a carboxylic acid. So if you wanted that carboxylic acid right next to that nitro group, this is a really good way to do that, where you can take your amino nitro derivative, and then once we hydrolyze this cyano group, it would take it off to a carboxylic acid. We can use it for other things like that. We can also reduce it down using lithium aluminum hydride to give us a primary amine here without actually reducing down that nitro group. So we can look for really cool specificity with direction in this particular reaction. So what else can we do with diazonium salts? I said before, we typically don't take ferric iodide and iodine. It's too endothermic, the reaction doesn't work, and therefore one way to get iodine onto this benzene ring is through this similar reaction right here. We create our diazonium salt, and in this case, we're using sulfuric acid instead of HCl, but it works the same way. And then we use potassium iodine as our source of our nucleophile iodine. It again generates nitrogen gas overall and gives us our substitution amine, again, exactly where the nitrogen was. There's no orthopara direction we have to worry about. Just like iodine was too endothermic a reaction to work for direct halogenation. The fluorination of this is very exothermic, and therefore it's very difficult to do it directly as well. We can do this using the diazonium salt, once again creating our in situ diazonium salt, but instead using this HBr HF analog here, or this fluoroboric acid right here. And what that will do is that creates a salt of our azide fluoroborate. Now, when we heat this thermodynamically decomposes into nitrogen and a BF3, but when it does that, it rearranges and leaves a fluorine on the ring exactly where the amine was again. So again, we get directed halogenation of our system, and now we can do all 4 halogens: fluorine, chlorine, bromine, and iodine. And it's all very directed. Again, we don't have to worry about ortho-para direction. Okay, so next on the list here is converting it to a couple other groups. One of the other groups we can convert it to is hydroxide. It's very difficult to get hydroxide exactly where we want it on the benzene ring, so just again, creating our diazonium salt with this and using copper oxide and water, we can generate the phenolic compounds right here. We can also use an acid form to get hydrogen where we want it, and we can use that to direct where we want things to be. For example, if we wanted the metabromo compound of toluene right here, if we just took toluene and brominated it, we'd get the ortho and para derivatives. If we nitrated it and then we looked at it, we'd again get ortho derivatives. So in this case, what we're doing is we're taking our amino derivative here, converting it to our amide. Once we do our catalytic bromination of it, we end up with our bromine in this ortho position to the amine right here. Once we get that orthoamine, we create our diazonium salt, and using our phosphoric acid and water, we can get rid of that diazonium salt, replacing it with a hydrogen, therefore getting directed halogenation of our toluene to that meta position, which we can't get directly. So this deamination reaction helps us, the amination helps us direct it, and then we can remove that amine, replacing it with hydrogen with the diazonium salt to give us our final product we're looking for. Okay, so once we form this diazonium salt, we don't necessarily have to displace it and actually remove it. We can actually add to it. And so once we have a 1R group on one side of the diazonium salt, we can add another group to the other side of it, creating a nitrogen-nitrogen double bond in between, and each of those nitrogens is bonded to one carbon. This functional group is called an Azo compound. And the cool thing about the Azo compound is now we have nitrogens extending the conjugation of the benzene rings. So in the case of something like this, where we take our diazonium salt, we react it with a phenol, it again reacts para to the phenol. And what that gives us is it gives us our diazonium salt with a phenol here, and that phenol acts as an electron donating group. That donating group changes the color of this azo dye. So in this particular case, this azo dye is orange, very strong orange color here. If we take that electron donating group and change it out with something else, we get different colors. Again, starting with our diazonium salt right here, instead of displacing the diazonium salt, we're going to add to it. We're going to get our diphenyl azo compound here with a different electronic drawing group. That different electronic drawing group changes the electronics of it. And while that extended conjugation system does create color, that change in electronics changes it from the orange color to a yellow color. So there's a wide variety of different groups you can use there, and you can change it all across the entire visible spectrum just by changing whichever groups is on that azo dye. Okay, another thing we can do with this system is use our nitrogen, or use our amine as a nucleophile. We've done this before in our SN1, SN2 reactions right there. And we know that if we have a nitrogen as a nucleophile, we can displace an alkyl halide to generate a secondary, tertiary, or even a quaternary ammonium salt, okay? Again, it's very difficult to to stop at a specific section, so it's not as synthetically useful. However, we can also acylate on these amines. The amine will act as a nucleophile and attack the carbonyl, displacing a better group. This is the way we make it amides in the carboxylic acids chapter. Now, because of the deactivation by the carbonyl compound, we typically get one substitution on the amide unless we do very rigorous dehydration to get a second one on there. So this is a very stepwise controlled reaction. So we typically get a single acylation on the reaction unless we do something very, very vigorous. Now, once we have that there, we can actually do some additional things as well, like dehydrate it or convert it back to other things, or like if we dehydrate it, we can convert it to a nitrile, or we can hydrolyze it off and go back to the carboxylic acid. All right, another thing we can do with these amine derivatives is we can do what's called a Hofmann elimination. Now, in previous reactions to make alkenes, we would do a dehydration reaction. And in the dehydration reaction, we go through a carbocation and we always get the more substituted alkene from the system, okay? So that would be following Zaytsev's rule. As an alternative here, instead of removing water during a dehydration, if we start with an amine and we quaternize it, we can actually get an anti-Zaytsev elimination reaction happening here. So let's go into that in a little more detail here. So if we have an aliphatic amino compound, we can react it with excess alkyl halide, and that'll turn it into a quaternary ammonium salt. Once we have that quaternary ammonium salt, we can react it with silver oxide. And so what that's going to do is that's going to react with the system, and it's going to get an alpha beta elimination to give us an E2 reaction. Okay, so if we think about it stepwise, we start with our alkyl amine, we make our quaternary ammonium salt. That makes this a very good leaving group. Then we can get a transfer of halides to give us the hydroxide here. Once we get this, we can get a beta elimination to give us our alkene and our quaternary, tertiary amine as our leaving group here. Okay, so what's so good about this is the fact that the major product from the Hofmann elimination is the least substituted double bond, okay? Because of the way it forms and because of the way it eliminates, it gives you a less substituted alkene. So if you want the terminal alkene, you want to try to create that secondary amine on your alkyl halide, generate your quaternary ammonium salt, react it with that silver salt to get to the less substituted product. If we just did our standard base catalyzed E2 elimination with an alkyl halide or a dehydration with water, we end up with the more substituted or Zaytsev rule product. Okay. So another way to end up with the least substituted alkene is to undergo what we call the Koch elimination. In the Koch elimination, what we do is we take that tertiary amine, and instead of taking it and making it a quaternary ammonium salt, what we do is we take it and turn it into an amine oxide by using peroxide or peracid. When we create this tertiary amine oxide, that makes it a really good leaving group because it's leaving as a hydroxyamine, and that's a neutral species, and therefore it leaves as that neutral product. Okay, just like in the Hofmann elimination, the Koch elimination allows you to lose this as a anti-Zaytsev product, and it gives you the least substituted alkene possible. And that is the end of chapter 20, amine.